We are given the laws of nature as differential equations or maybe iterative maps. This is a short-time description of dynamics. This tells us what happens for infinitesimal or short time. What we would like to understand is the consequences of dynamics at long time, even infinite time, time much beyond Lyapunov time. The connection between short and long time, you're actually familiar with from quantum mechanics and other subjects. That's what Fourier transforms do. If you have some short distance information, then Fourier transform variable will tell you what happens at long distances. In this subject, the transformation comes in two flavors. One is if you have discrete time dynamics, the transformation is called a generating function. Not very illuminating, but I'll go step by step and you'll see what I mean by that. And in continuous time, you're very familiar with it because it's just a Laplace transform. So I will first explain in this video how it works for discrete time, and then in the next video I'll show step by step in parallel how this works for continuous time. So in discrete time, the main object will be called generating function. So we start by a coarse-grained partition. Meaning that we divide our state space into M regions, which we label arbitrarily M1, M2, to MM. And the simplest dynamics is counting dynamics or topological dynamics. That's given as a one-step transition matrix, which is defined as a matrix that has an element 1 if transition from Mj to Mi in one time step is admissible, and 0 if it's inadmissible. Now, what is the meaning of T square Ij? That is to say, I start in J, I go to K, some site in a partition, then I go from K, and I go to I, some of our intermediate states. Well, this gives me 1 for every admissible walk. So this is number of walks from J to I of length 2. And similarly, if I apply this operation n times, this is the number of walks of length n. Now, this is just counting, but what we really care about in dynamics is not so much counting, but also likelihood that something happens. And that's very easy to understand also on topological level. Consider state space. So here is a state space. That's state space M. And within this state space, there is a partition which we call Mj, and there is another partition which we call Mi. And now what does dynamics do? It sends points here someplace into the space, so that happens after under one iteration in time. And it maps this whole region into some region in state space. And that region in general only intersects in a small part here. So when we start in Mj and we want to find where we got into the other region of the partition, we obviously want to know what this intersection is. So we need to modify our transition matrix to something maybe that's called transfer matrix. Lij, which is 0 if it's inadmissible, but it's some number in reals which says what fraction of points that started here ended up in J. So we really need to modify our transition to describe some kind of likelihood of transition. Saying just 0 and 1 is a little bit too crude. So here is the simplest thing that we can do. Instead of computing these probabilities, which we can do, of course, but let's take a very simple assumption. Let's say that typically there's some fraction that makes it from one region to the other, and the simplest thing is to assign equal probability or fraction. Equal probability. And again, you have to understand in deterministic dynamics, there is no probability. This is just a way to think about it. For every admissible step. So we'll give it some number, C, and we'll make that number anything. If it's 0, of course, it's boring, nothing happens, but if it's larger than 0, it's interesting. And intuitively, it should be something smaller than 1, but it'll turn out to be something more interesting. So for n discrete steps, the likelihood is 0 to the n. So now we can compute a total probability for transition starting in region J and ending in region I as probability that we go one step, probability that we go 2 steps, we have to pay penalty z squared for that, t squared ij. Probability that we go 3 steps, t cube ij, and so on. Now this is a geometric series. So I can write this Fz, one transition, all walks of like 2 between, all walks of like 3, and so on to infinity. It turns out that what you care about is actually infinite behavior, but this is geometric series, so I can write Ct 1 minus Ct. I can sum up. Remember, with matrices, I can do everything that I can do with real numbers. Ij. So now, this is a formula that says that if I know something about the transfer matrix, for example, I bring it to a basis where it's diagonal, etc., I can compute the probability that I go from region I to J in all possible times. So total probability of transition. And this is an example of a generating function. So the generating function Fc is some polynomial in Zn, n goes from 0 to infinity, typically Fn. So we have transformed something that is function of this probability of a single step to something that's a F expansion, not a Taylor expansion, but the generating function expansion of the same quantity. And on the right-hand side, we gave you a rule how to compute this. This we computed from T one-step dynamics to the nth power. And on the left-hand side, this is sum of all possible behavior. So this is exploring long time, n goes to infinity behavior. Given short time, n goes to 1 behavior. Well, n equals 1 from one step. And as we'll see, this can be thought of as a discrete Laplace transform. This is not obvious now, but as soon as we go to continuous time, it'll be pretty obvious. Let me summarize what we have learned about discrete time dynamics. We live in some state space. State space M. And we have partitioned it, coarse-grained it into regions of which I only write the initial and final for the transition we're interested in. And then we are given a law of dynamics which says if I start someplace here and if I land there, that's given by my short-term dynamics in detail. But when we look at coarse dynamics, we have replaced this detail law which says how you start from the point and end the point. We replaced it by the transition matrix. This is one time step, shortest possible time step dynamics. But now, we also have description of long time, which means that if I look at the state space and I explore it with its partitions, I explore it by trajectories of long or infinite length, which means I do something like that. And I do this forever. So I get totally crazy dynamics, ergodically exploring every place. This I can describe by a generating function. Z t 1 minus ct. And now this generating function, the transfer matrix has a spectrum of its eigenvalues. And clearly, this thing will be divergent as long as my probability of hop is smaller than the inverse leading eigenvalue of this. This is a convergent series. And as I approach it, I will actually start sensing what happens in long time. So this gives me the infinite time dynamics. So this is how one thinks of going from, in discrete time, from one step to infinitely many steps. And the main trick is just to resum all possible paths using generating functions. What we'll do in the next module is we will do the same for continuous time.